Thanks everyone for attending. My name is Argyrios Kyrgiazos and I work at CARTO as a data scientist. And today's my presentation is about how we build a global spatial model in order to classify the urbanity levels in territories. So basically the agenda of this presentation is first like, okay, what motivates us? What is the questions that we try to answer? How we answer, what are these urbanity levels that we consider, the classification, the labeling that we proceeded, what data we use for that purpose, the challenges we encounter and how we overcome them. Then a bit more about the methodology and also the challenges, because this is a global model, and so how we were able to scale it globally. Then a few results, like a few maps results, and then examples, and then I conclude with this presentation. So first of all, I mean, based on US Census Bureau, we see some very interesting statistics as like 80% of movers stay within the same metro area, some within 8% within the same state, some others like 6% stay within the top 50 metro areas, and then you have a very small percentage that they leave these macro areas. All these changes, and this is just a very small example of the changes, like some statistics regarding movement. All these changes and all these trends in mobility in between urban territories, they have a huge interest, and huge impact on logistics and commerce, how we can optimize the supply chains in order to optimize efficiency and cost, telecom rollout, how we can optimize the network planning in order to make it more efficient and address the needs of the user better, CPG and retailing, how we can address better the promotion based on the territories. If you have a very high density area, more people, or more far away area from the center, what are the habits of the user and so on, in real estate, of course. So all these changes and trends we want to monitor somehow, but also we want to classify territories based on the urbanity topology. So this is what we try to answer. So how we can come up with the classification for the different categories, so where somewhere is, and use that for a number of cases. So for that purpose, what we did was that we built a global spatial model in order to provide urbanity level for at a very high granularity. The granularity was we use a spatial index quad key at zoom level 15, where basically each cell has 1 by 1 kilometer at the equator. Going more granular than that, it was very, very fine granularity, and through our research we found that this level 1 by 1 it was more appropriate to meet most of the needs. So how we can classify territories based on the urbanity topology? Having gone through the literature and doing our own research, we came up with 6 different urbanity levels that would help us classify the urbanity. So starting from the lowest, I would say, which is remote areas that they have very low or no population and they're not easily accessible through the main road network. So basically these areas are mountains or deserts or this kind of territories that they're not easily accessible and you cannot access them by the road network. Then we have the rural territories that they have a very, very low population, but you can access them through the road network. So basically what it differs from the remote areas is that rural areas, we can access them through the road network, but this has nothing to do with using the land for farming purposes. So we use the term rural, but we don't refer to farming purposes. Then the third one is low density urban areas. So basically here, compared with rural, we have more population, but they're more sparse. So So basically, we try like to label like small, medium towns or villages with this label. Then medium density urban, yes, a bit more dense populated areas. And then we start seeing more like concentration of nighttime light data. So we see more activities into these areas, outskirts of big cities. The fifth one, high density urban area. So again, now we start talking about large cities, center of important cities. So basically, we have a very dense populated areas, and we see very high concentration of activity into these areas. And then the last, basically, we're talking about the very high density urban areas. So metropolitan areas, so the big cities, the capital of each country, where basically most of the population is concentrated and most of things happen. So in order to come up with this labeling, we had to select some data sources in order to assist us to achieve this purpose. So one challenge that we had to overcome is that we had to use data sources that they were available globally and that we were confident that the quality was good enough to use in each country. So for that, we came up like with 3 data sources. So basically, the first one was population from the World Pop, which was provided at population grid at 1 kilometer resolution. On top of that, we had nighttime light data. So basically, this is the annual intensity of nighttime light data from monthly count-free average radiance grid, and the resolution for that, it was approximately 500 by 500 meters at the equator. So from what we see in the literature, for these 2 datasets are highly correlated, and the reason that we selected the 2 of them was so each one of them to complement the other. So, for example, in some cities, like we have like very high population density, some like in the cell, and then in the adjacent one we have very little, just because it's a park. Like it's an area that doesn't have so much population, but it's right in the city center. So for that purpose, we use also nighttime light data in order to combine this information and also to be able to differentiate the urbanized areas. So, for example, areas where we have very high population, but in some areas we have higher activity. And the third dataset that we used was the road network, and for that we use only 5 different road segments, the ones that we were confident that the availability and the quality was good enough. So basically we used like the highways, like primary, secondary, motorway, and truck road. So we use these data sources, and basically we had to combine all of them at a global level. Now so this is like an example, like how it looks like by putting these 3 data sets all together. So this is what you see is like London, basically, and on the left side you can see the population density, on the middle the nighttime light data, and on the right the roads length. This is just an example of visualization of by putting the 3 data sets together. So first challenge that we had to overcome is that, as in many datasets, what you tend to have sometimes is some outliers. In our case, the outliers was with the nighttime light data. It was that at specific places we had very high intensity of the light data that would not follow the rule, like the higher the population, the higher the light intensity. And that was due to the fact that some power plants of some river data, for some reason, had a very high nighttime light intensity, and this was breaking the relationship between like population and nighttime light. So for that purpose and for these areas, we had to go and fix, in a way, the light data. So how we did that? Basically, we identified these local outliers, and after we identified, basically we built a simple like regression by using the population and the lag population of the surroundings. And we replace these values, the outliers, from the ones coming from the prediction, from the regression. And an example can be seen like here, like on the left figure. This is the initial case, like we have on the horizontal axis the lie data, and on the vertical the population density. And the orange one were the outliers. So basically we had very low population, but very high intensity of the lie data. So this basically, we impute the new values for that, and the outcome was the one that can be seen on the right. So we brought back the relationship between population and nighttime light data. Now, having done that, having fixed data, making sure that everything is fine, then basically what we did, we proceed with the modeling. Now, one very important thing about this spatial model, which is a global one, each country has its own classification. By its own classification, I mean that we proceed with the labeling country by country. And the reason that we did that was you cannot really compare like some countries, the countries between them. So for example, you have like Greece, where you have like some population, then you have China, you have New York, you have Spain, where basically if you try to compare like the population density in New York with the population density in Madrid, basically everything, it's not going to be very high density compared with New York or what you see in New York. So in order to be fair in a way, we decided to go to country by country. So overall, the methodology that was followed country by country, and as I said, the model was run per country, was first that we had to gridify. So as I said, we use a spatial index of 1 kit at zoom level 15. Then we brought all the information, we enriched this data with the information, with the population, the light data, and road network. And then the first step was to generate one index by using the population and the nighttime light data. So with that, basically we call it this urbanity index, where basically it shows like the higher the index, the higher the urbanity level should be. And because we do like a spatial model, we cannot ignore what happens in the surrounding of a cell. So for each cell, we had to also consider what happens in the surrounding. And for that, using on this index, we perform like the get-sort statistic calculation and using 2 layers of information. So for these 2 layers of information, essentially what I mean is, as an example where you can see on the right, you have like the central cell, and then you have the layers of the rings around it. So for that purpose, what we consider is that 2 layers. So basically going like 1, 2 layers. So we consider this information for each cell in order to calculate the statistic. So this statistic, what it gives you like a Z-score. So basically it gives you like one index and tells you like the highest it is, the more urban, the lowest, the less urban. So for that, what we did is that we quantize it. So we quantize it, and then basically the higher QVADA was the higher urban, and the less was the less urban. But that was like the first step of the whole process, and it was followed by a second. So for the rural and the remote, in order to get better classification, because as you remember, essentially the main difference between rural and remote, it's not only the population, but it's the access to the road network. So for these two areas, what we did is that we repeat the same process, but this time using the road network. So we perform this, again, the calculation of this get-sort statistic on the length of the road within a cell, but this time using 4 layers in order to make sure that the further you need to go further away from a network in order for an area to be considered as remote. So again, we did like a cluster on this, and then basically we used the lowest cluster of this new z-score to label the cells as remote. And then some final refinement on the cells, just making sure that you have one cell and all the surrounding cells, if they have the same label and the one in the middle has a different value for any reason, just make sure that everything is consistent. So we had to change the value of the cell in the middle to the one of the surroundings. So that was the final refinement. Now, very important thing is that, for example, the steps of gridifying and enriching the cell and calculating the Getty sort statistics, these were very intense calculations, especially for big countries such as Russia, Canada, Australia, USA, and so on, where we had like millions, tens of millions of cells, and we had very intense calculation. These operations they were performed by using CARTO's analytics toolbox by taking into advantage the scalability that it was provided, and we were able to perform effortlessly these very complex and very intense computations. So by doing this process overall, we were able to obtain the labeling of urbanity for each country, 252 countries overall. It was quite intense, and basically one example for UK, you can see here. So basically the deep red color is like the very high density, then the yellow is less high density, the green rural, and the deep green is basically remote. So you can see some examples here, but all this information also was provided like in a blog post where maps are available. So basically the users can go there and navigate, have a look how it looks like, and so on. Now, gathering some statistics regarding urbanity level by continent, what we saw that for most of the continents, like the greater percentage was remote. So, for example, for Africa, I mean, too many forests, so you had too many remote areas. The same for Asia, North America, Oceania. But as we can see for Europe, which is like more urbanized, like we see a lowest percentage of urban areas. Now, some other statistics by regions, what we can see that for US, we can see that 66% is remote and only 0.07 is very high density urban areas. While if we go to Western Europe, we see that it's 0.2% it's very high density urban areas and only 68% it's remote areas. This is some interesting statistics that we also use for like evaluating the performance and the validity of this model that we built. Now, urbanity level now, this is available at CARTO Spatial Features. CARTO Spatial Feature is basically CARTO's very derived dataset that it can be used to boost spatial modeling, available along with population, point of interest, elevation, and climatology. Now, urbanity level is one of them, and is available at quad key 15, and then we downscale it also to 18, and it is also available at H3 index and resolution 8. So this concludes my presentation. Thank you very much for listening and paying attention. I'm very happy to answer any question you may have.
Awesome. Thank you, Argyrios. It was really great to hear in depth about the methodology and the results of your spatial model to classify those global urbanity levels. If anyone has any further questions, please feel free to connect with Argyrios either on LinkedIn